Section 5.4, we don't have any new theorems that we need to learn. The idea behind this section is to learn how to apply the integral in a few different contexts. So let's look at some examples. In this first example, suppose a particle moves on a line with a velocity given by v of t equals 3t minus 5. T is measured in seconds, and the velocity v is in meters per second. So we're going to have three things that we need to do. First, we're going to find acceleration and position functions of the particle. The second thing that we're going to do is find the net displacement of the particle from time 0 to time 3. And the third thing we're going to do is find the distance traveled by the particle over that time interval 0 to 3. One of the things that I want you to notice is that B and C, we are asked to do something that sounds exactly the same. So we're going to talk about the difference between displacement and distance. These time intervals, t equals 0 to t equals 3, and the intervals 0 to 3 have the exact same meaning. Let's start with finding the acceleration. Acceleration a of t is the derivative of velocity. So when we differentiate velocity, we just get 3. So the acceleration is a constant function, 3. To find the position function, I know that the derivative of position is velocity. So if I anti-differentiate both sides, position is the antiderivative of velocity, the indefinite integral. So we're going to integrate 3t minus 5 dt. Oops, put a dv on there. That should be a dt. When we take the integral using the power rule, we add 1 to the power, divide by the new power. The constant gets a variable tacked on, and we have a plus c. So we have 3/2 t squared minus 5t plus unknown constant c. In this example, we don't have an extra piece of information to solve for c, to solve the initial value problem. We're not told where the position starts. So this is as much information as we can give about the position of the particle. But if we were given that position at time 0 was blank, then we could use that information to solve for c, like we did in section 5.3. So here's our acceleration and position functions. For part B, find the net displacement of the particle from t equals 0 to t equals 3. What I'm going to do is look at where is that particle at those two different times. We have a tiny bit of a problem because our position function has this plus c in there, but it won't matter for this example. What I want to do here is just figure out where is the particle at time 0 and where is it at time 3. And for the net displacement, I'm just going to look at the difference between the two. So we can just look at s of 3 minus s of 0. So let's compute those separately. S of 3 is 3/2 times 3 squared minus 5 times 3 plus c. 3/2 times 3 squared is 27/2 minus 15 plus c. 15 is 30/2, so I have negative 3/2 plus c. S of 0 is 0 minus 0 plus c. So plugging these in, we have negative 3/2 plus c as s of 3, and s of 0 is just c. So we end up with negative 3/2. Another way to do this problem, another way to get to the same spot, we could have used the integral, the definite integral, from 0 to 3 of v of t dt. It's a little less obvious to set up, but it gets us to the same spot. Now, the net displacement here is negative. The units are meters. So what we need to do is figure out what does that mean? Does that even make sense? So if I think about this particle, at time 0, it was somewhere. And at time t equals 3, it was 3.5 meters less. So if I'm labeling things on a number line, that's going to be 3.5 meters to the left. I'm sorry, 3/2 meters. So what this means, this negative value just means that we end 3/2 meters to the left of where we started. Net displacement doesn't track where the particle is along the way. It's just looking at where you start and where you end. So for example, if you were to walk in a circle, your net displacement would be 0, even though you have traveled a distance. So now let's look at distance traveled. Distance traveled is a little bit more tricky because if the particle is moving in more than one direction, we want to add those up separately because in displacement, they get canceled out. So what we need to do is figure out which way the particle is going. We're going to start by solving for when the velocity is 0. Okay. So our formula for velocity is 3t minus 5. So 3t equals 5. So t is 5/3. Okay, so if I treat this like we did when we were graphing, make a number line, put my 5/3 on there, I could figure out which direction the particle was going by plugging into my velocity function. So if I look at something to the left of 5/3, say 0, when I plug in 0, I'm going to get 0 minus 5, which is a negative. Okay, so the velocity is negative here. When I put in something bigger than 5/3, say 2, I'll get 3 times 2 minus 5. That's a positive. So that tells me that before we have time 5/3, the particle is moving left. And after time 5/3, the particle is moving to the right. So if I want to find out how far the particle went from time 0 to time 3, what I'm going to do is add those two distances, the distance moving left and the distance moving right, separately. So to find the distance moving left, what I'm going to do is figure out s of 5/3 minus s of 0. Because this is distance, I'm going to put this in absolute values, because if we end up with a negative, I don't want a negative for distance. So plugging 5/3 into my position function, we get negative 25/6 plus c. And as we already know, plugging 0 into the position function, we just get c. The c's cancel. So we just have negative 25/6 in absolute value, which is 25/6. So that's, in meters, the distance that we moved to the left. Now we find the distance moving right. So we'll have s of 3 minus s of 5/3. Earlier we found that s of 3 was negative 3/2 plus c. S of 5/3 is negative 25/6 plus c. Once again, I have a plus c here, and when I distribute the negative, we'll have a minus c over here. The c's will cancel. Negative 3/2 plus 25/6 will give me a positive 16/6, which is 8/3, and because it's positive, I don't need absolute value. Although maybe it would be more useful to leave it as 6, because next we're going to add these two together. So the total distance traveled is going to be 25/6 meters plus 16/6 meters, which will give me 41/6 meters in total.